Now, I'll show you how to perform two sample t-tests in R. I'm going to use the births dataset. The book we're using has its own R package. To use a package, you have to install it. You can run this line of code here, just get rid of the note character, or you can go under Packages, Install, and then look for it. You only have to install a package once, but whenever you want to use it, you need to initialize it using the library command. If I run this head births, I get an error, and that's because I haven't run the library command. Now it works. This head command shows me the data. The two variables I'm interested in are weight, which is the baby's birth weight, and smoke, which tells us whether or not the mother was a smoker. I want to perform a two-sample t-test to see if there's a difference in birth weight between these groups. First, we check our assumptions. Do we have two independent random samples? I guess, assuming they randomly sampled from the two distinct populations of smokers and non-smokers, we should have independence, so that the weights of the babies in the smoking group are independent of one another and the weights of the babies in the other group as well. The other assumption is that our groups will have normal means. So we either need a sample size large enough for the central limit theorem to kick in, or we need these values to look like they come from normal populations. I can use this square bracket notation to subset elements from the data. This line is saying, tell me the number of elements in births dollar weight where the smoke variable is smoker. So it's telling me how many babies had smoking moms. And this one tells me how many babies had non-smoking moms. Our sample sizes are big enough that we can assume normality, but let's draw some histograms anyway. They both look somewhat left skewed, but because of the large sample sizes, the means should be normal, and that's what matters for the t-test. Our assumptions are met. We're testing for a difference, so this is a two-sided test. Our null hypothesis is that the difference between the population mean birth weight of babies whose mothers smoked and the population mean birth weight of babies whose mothers don't smoke is 0. The alternative hypothesis is that this difference does not equal 0. By default, mu is set to 0 in R's t-test command, so we don't need to put mu equals 0. We use this squiggle notation similar to what we did with the box plots. And the result is a p-value of 0.138. This is fairly high. It's higher than 0.05, so we would not reject the null hypothesis at the 0.05 level. We conclude that there is no difference in the mean weights for these populations. Recall that the t-statistic for the two-sample case looks like this, and mu1 minus mu2 equals 0 under the null hypothesis. So the numerator is based on x bar 1 minus x bar 2, and the denominator is always positive. This means that the sign of the t-statistic will tell you which direction R is subtracting. In the R output, the t-statistic is positive. The sample mean of the non-smoker group is higher than the sample mean of the smoker group, so we can tell that R is subtracting non-smoker minus smoker. When we're doing a two-sided test, The p-value will come out the same no matter which direction you subtract. I set up the test as smoker minus non-smoker, and we get the same conclusion. But we need to pay attention to what R is doing in order to interpret the confidence interval. We are 95% confident that the mean birth weight for babies whose mothers did not smoke is between 0.13 pounds less and 0.93 pounds more than the mean birth weight for babies whose mothers smoke. And the confidence interval agrees with the two-sided test. The null value of 0 is within the 95% confidence interval, so we do not reject the null hypothesis at the 0.05 level. Here's what happened. The t statistic lands here. The area less likely than that would be this area here, and then we double it to get the p-value. That was a two-sided test. For a one-sided test, where the alternative hypothesis is that the non-smoking group weighs more, you would set it up like this. This time, the direction I'm subtracting agrees with R because the p-value is affected by the direction. So it is very important to check your data to see in which direction R is subtracting. The t statistic is the same, the degrees of freedom are the same, but the p-value is half of what it was. And that's because we're only concerned about t statistics that are greater than what we got. The area we care about is this. If our alternative hypothesis was that the non-smoking group weighs less, then again, we'd have the same t statistic, same degrees of freedom, but now the p-value is based solely on t statistics that are behind what we got, because what counts as more extreme than what we got depends on the alternative hypothesis. R has a built-in dataset called sleep, where 10 people were each given 2 drugs, and the amount of excess sleep that they got compared to a control is in this dataset here. The ID variable keeps track of the 10 subjects. In this case, each person is in both groups, so we do not have independence between the groups the way we did with the babies. For example, notice that subjects 6 and 7 have high measurements in both groups, and subjects 4 and 5 have fairly low measurements. You would get a bad estimate of this variance if you took these measurements to be independent. But we do assume that we have independence within groups, which means, for example, that these subjects 4 and 5 don't affect each other's measurements. Within the groups, everyone's independent. Our null hypothesis is that the difference in mean excess sleep among people taking these drugs is 0, and our alternative is that it is not 0. I'm doing a two-sided test now. A paired test is a one-sample test on the differences, so you treat the set of differences as its own data. Instead of having 20 measurements, I have 10 differences. That's what I'm doing here to check the normality. I'm storing the differences as diff. Then I'll check the histogram. Because the sample size is so small, I want this to look normal, and it looks all right. We have this one outlier, but it doesn't look too far away, and it's such a small sample that I'm okay with assuming this was drawn from a normal population. The t statistic is negative 4.0621. The p-value is 0.002833. That low p-value gives us strong evidence that the null hypothesis is not true. It doesn't list the means though, so we have to figure out how it's subtracted in order to interpret this confidence interval. It looks like mean of group 1 is lower than mean of group 2. The t statistic is negative, so R is subtracting group 1 minus group 2. I think it will always select the first group, but I can't be sure. You should always check this. We are 95% confident that the mean difference in excess sleep time, drug 1 minus drug 2, among patients who take the two drugs is between negative 2.45 hours and negative zero point 0.7 hours. Because both those bounds are negative, it's saying that drug 2 gives more excess sleep than drug 1. We get the same result doing a one sample t-test on the differences. When we do a two sample test, we get a completely different result. We would not want to do the two sample test here because the two sample version assumes independence between groups, and we don't have that here. And then finally, here are the one-sided versions. I did the less than version in the lecture. If you do the less than direction, the p-value is 1/2 the two-sided version. When you do the greater than direction, you get this, where the p-value is almost 1. In this test, we would fail to reject the null hypothesis, and our conclusion would be that the mean population difference is 0. If you begin with this test and fail to reject the null, you should not go and do the other direction or the two-sided test, which would give you a significant result. That's called data snooping. You need to specify the direction of the test before you perform any calculations.